This episode is sponsored by Audible. For thousands of years, humans have sailed ships through Earth's vast oceans, navigating by the stars. Someday, we might sail the stars themselves. So today, we return to the Generation Ship series to finish out our recent look at colony ships of truly enormous size. As we mentioned earlier in the series, in Million Year Arc and again in Planet Ships, if you have to contemplate truly long voyages, not just of a few generations, but potentially astronomical timelines, you have to plan for a level of redundancy that safeguards your colonist's survival, even if their society collapses and rises again several times along the way. A few centuries is a fairly fast trip to even nearby stars, and it's also a lot longer than most civilizations have lasted, at least in the sense of continuity of goals and focus. Now there are some exceptions to that, and one is where the goal or focus is simply survival, as civilizations replaced or mutated with time keep basic goals like that, and if you're on a generation ship, that mission is basically survival. You aren't necessarily limited in options to only surviving the trip to a new system and surviving that system's colonization, but close enough. That goal, colonization, can be more easily maintained in the long term because it so closely mirrors our normal survival motivation. In addition, we shouldn't overlook that we might have much longer-lived civilizations simply because, in the future, we might get better at it and have longer lives. Additionally, civilizations often collapse from external pressures, usually intelligent ones, if they're advanced enough to be resilient to natural disasters, and a colony ship has little external pressure. However, exceptions go both ways here, as on Earth if a civilization buckles, its neighbors can fill the gap, and surviving remnants can rise back up again. On a long enough timeline, even a total species extinction might see another one evolve intelligence and technology. On a spaceship, both of these are less likely, as the spaceship needs maintenance and is generally too small for much redundancy and diversity, at least in ecological and cultural terms. We discussed lots of workarounds to those sorts of problems earlier in the series, but last time we also argued that for truly long voyages, to other galaxies for instance, which might take many millions of years or even billions, you'd need a model for a spaceship that can survive that long, and the only example we've currently got is Spaceship Earth. The closer you can get your spaceship to being a planet, the more durable it is in virtually every respect. Of course, the Earth is not strictly speaking capable of independent survival. It relies on the Sun for power, and this of course leads to part of the reason this episode is named Fleet of Stars. We have a lot of ways to move a star, and a lot of reasons to want to move one or several, and we'll look at those today. But there's a second aspect of that name I want to comment on first. A point we've made before, most recently in Hitchhiking the Galaxy, is that transporting people over interstellar distance is very energy intensive. The amount of power needed to push along spaceships that might hold several thousand people at an acceleration rate of 1g is, depending on how spacious the ship's accommodations and cargo holds are, either enough to easily power our entire modern global economy on the modest side, or enough to light the entire planet up as a second sun. As a result, not only might travel to other worlds be frowned on as wasteful of energy beyond initial colonization, and because ships with such energies are effectively doomsday weapons, but also because of sheer light pollution. If you've got thousands of big ships going to and from your solar system on any given day, it is going to look like a literal fleet of stars. Science fiction often fudges scale by letting us see spaceships from the cockpit or bridge window of a ship they are fighting, which is highly unrealistic, but only in terms of making them out, when they'd probably just be radar blips. In terms of brightness though, they actually would look like bright little blips when their engines were on, even millions of kilometers away. Nobody would ever need a telescope to see a bulk freighter decelerating as it approached their system, let alone their planet. But getting back to the energy wastefulness notion of interstellar travel, we often point out that it's enough energy to accelerate one person up to relativistic speeds as it is to keep someone alive and in luxury on a planet or space habitat for 1,000,000 years or so. Thus, a lot of cultures might frown on casual travel. As we've noted before, this doesn't apply to colonization, since you can grab orders of magnitude more energy by going to a new and unused system. It's a huge investment of energy, but for a vastly larger reward. There's an implicit assumption, though, that these trips are way shorter than 1,000,000 years, and that life support on such ships is a tiny fraction of their total energy budget, being the same as what folks on a stationary space habitat back home would use. Thus, while bigger is better for spaceships, you also want to go as small as you can too, to save energy, and not even colony ships or drone fleets for harvesting distant stars are exempt from this. When we start contemplating really long trips though, not only is the bigger is better concept far more true, but that cost to get up to speed is no longer an overwhelming factor. The trips are just so long that the life support energy costs are no longer a drop in the bucket compared to energies needed to speed the ship up or slow it down. And as we noted in planet ships, for very large ships, you don't slow them down. You just send fleets of colonists out from that gigantic ship to nearby systems as you fly by. Now, the obvious assumption, especially given the title, is that it needs a power source, and Earth's power source is the sun. So we need to send a sun with a planet around it instead. But realistically, not so much. We can do that, and we'll get to explaining how shortly, but when we say a planet ship, we are still talking about something very artificial, even if for no better reason than you need protection against all the radiation and debris you'd be hitting at relativistic speeds during your interstellar journey. You might give these things sunlight and make them spherical, but it's going to be an artificial sun. We do have a motive for moving whole stars as ships, but not just to move a planet. It would be like picking up a mountain a house was built on instead of just moving the house to a new mountain, or just its occupants and their prized goods. If you just want to move a house, move a house. If you just want to move a planet, move a planet. Channel regulars, of course, already know we've got plenty of motivations to move entire mountains, or entire stars too, and we'll review some of those and introduce some new ones. First though, let's get to the how-to. The first, simplest, best known, and worst method is the Shikata thruster. For a given value of best known anyway, the Shikata thruster is a decades-old idea, but it's only recently got much attention. Of course, the others are even less well known, so much so that I'm stuck naming them, and am just assuming somebody else thought them up before me. We'll get to those, but what is a Shikata thruster, and why is it both the simplest and worst star drive? We'll keep it short since it does have its own episode, and for that matter, one of the regular editors here, Greg Leal, made his own video on the topic last year too, and we've other material to cover. A Shikata thruster works on a simple principle. Stars emit light. Light has momentum and can be used to push things, as we often discuss here, but by default, a star emits light omnidirectionally, and even when that's not uniform, it tends to be symmetric, like emitting more from the pole for something like a neutron star, but both poles, so they cancel out. The handy thing about light is the photons making it up are the absolute best rocket fuel in terms of achieving the maximum final speed. They are also basically the worst for acceleration, and a star is already a very heavy thing to be trying to push on, so Shikata thrusters are slow as heck to get going, though obtain a fairly decent top speed in the long run. The advanced technology employed to move stars, something most science fiction writers would view as Clark Tech, so advanced only godlike aliens could do it, employs an ultra-sophisticated device known as the Stellar Photon Reflector, or more commonly, a mirror. Or actually, any fairly shiny bit of metal will do. It need not be something good enough to shave in. The two tricky parts are, first, you do need a lot of them, and second, you need to coordinate them all so they don't smack into each other or fall into the star or off into deep space. See the episode for the specifics, but one bit that often confuses people is why the star moves. You have to add up all the forces involved. Some of the star's light flies off in the right direction, applying force. The rest flies off and hits mirrors, which bounce it in the right direction, and the whole system gets its thrust this way. Those mirrors are absorbing a lot of momentum, but they are also being pulled by gravity, that star's gravity, and the balancing act is making sure the light force on them, the radiant pressure, is the same as the gravitational force on them. Those mirrors, though vastly smaller than that star, exert the exact same force back on it, and so the mirrors are actually gravitationally tugging that star toward them too. Amusingly, since gravity and light both fall off with the square of distance, it doesn't actually matter where you put those mirrors, so you'd presumably put them as close as they can be without melting the mirror or slagging the control mechanisms on it, to get maximum reflection for minimum mirror mass. If that's all you're doing, then any planet around the Sun can be dragged along, but are probably going to need pushing on too. But the Sun is so much more massive than them that it's fairly simple to direct enough momentum their way at the right times to keep them attached to that star and in the right orbital paths. The advanced technology for this is in the accounting department, because you've got to be constantly keeping an eye on everything's momentum and tweaking things before they get perturbed and need bigger pushes to fix them and everything else they perturbed in turn. So why is it slow? In our discussion of using solar sails or laser sail spaceships, we've often noted that you need 3 gigawatts a ton or 3 megawatts a kilogram to push an object with light at an acceleration of 1g, Earth gravity. Assuming your Shikata thruster was perfectly efficient, all light eventually ending up headed the right way, our own Sun, massing 2 times 10 to the 30 kilograms, would need 6 times 10 to the 36 watts of power, 6 trillion watts, to accelerate at 1g. The Sun is hugely powerful, but nowhere near that powerful, having a luminosity of 3.8 times 10 to the 26 watts. It would need to be 16 billion times more powerful to get that 1g or 9.8 meter per second acceleration, so instead we'll accelerate 16 billion times slower, or about 0.6 nanometers per second, which is quite slow, and the usual concept assumes you only get to thrust with maybe half the total light, so it takes you a million years just to get our Sun up to 20 meters per second. Of course, in a billion, it could be doing 20 kilometers per second, and would have covered about a third of the galaxy. A few notes: bigger stars than ours are far more luminous per unit of mass, and thus accelerate much quicker, but can't accelerate as long and explode. Smaller ones than the Sun go slower, but can achieve a far higher top speed, as they burn all their fusion fuel up and can live trillions of years. This means if you need to move stars in a hurry, like a nearby one is going supernova, you build your thruster around that big star instead and divert it, and if you want to travel to another galaxy, you pick that smaller star. Now you can potentially speed this up a bit by directing light back down on that star too, heating it up to produce more light, but the better aspect is this takes us into a second and faster way to accelerate, a type of star drive which I'll just name the Helios Drive, as it's more like a big sun chariot anyway, and I've never heard another name for it. The Helios Drive adapts the technology we discussed in our episode on starlifting, our trick for mining stars. Here though, instead of reflecting light down and magnetically steering it to blow off the poles for collection, We instead turn it into a big pair of rocket engines, then we magnetically flip one of them back down so it's only shooting one way. This is now a giant plasma rocket engine, and it is going to let you accelerate far faster, but at the price of a lower top speed. You're shucking off matter to do this, not just pure photons, and it is basically going to follow the rocket equation for a fusion torch drive. You're starlifting so you can throttle it too, getting up to speed in say 1,000,000 years, throttling it down or packing it up till you approach your destination, then unpacking or ramping it up again to slow back down. Ideally, you'd probably want to entirely englobe the star, and coming up with material for that is no problem since again, this is the same technique used for mining materials from stars anyway. Interestingly, the timelines involved would mean a small initial colony could reach such a star and grow to be a K2 civilization, one that englobes a whole star, before it arrived at its destination, presumably a very distant part of our galaxy or another one. Also, since you can use this technique to purge stars of poisonous materials like helium, you could be gobbling up material from other stars or gas giants to use as extra propellant and fusion fuel, and thus get a higher final speed out of it, another fleet of stars. We have a few more ways of doing it better though. One, like the Helios Drive, sacrifices higher speed for a faster acceleration, and that's the Nova Drive, and its big brother, the Supernova Drive. If we take a stellar remnant, like a white dwarf, we can dump hydrogen on it and get some fast fusion. Dump too much too quick and you get a nova, the regular old kind. Dump a lot more on one, and you get the far more energetic Type 1a supernova. It's a lot of energy and released quite quickly, even just the nova version. Containing and directing that as thrust, and releasing it slow enough to be thrust rather than smashing everything, is no mean feat, and we discussed how that might be done in March's episode, Civilizations at the End of Time, Dying Stars. Fundamentally though, it's the same concept as a post-nuke spacecraft like the Orion, which shoots nukes out the back and rides the blast, obviously scaled up a lot. However, in black hole ships last week, we discussed various ways to use black holes as ship drives, and even very big ones, and one of those methods was what we think power quasars, thus giving us the obvious name of a quasar drive. This method is truly the best star drive, even if like the Nova Drive it is technically using a dead star, because it produces a vastly higher mass to energy conversion ratio, and is basically a giant photon drive. And this is the behemoth we will want to use to move stellar masses around. It's also the most massive and most efficient of the types we've discussed, as the power source is more efficient than fusion, allowing a higher top speed, and can be throttled, since you can add mass in or not. Needless to say, you don't live very close to the engine, but that's true of all the others, and honestly, normal ship drives too. Handily, it's also one we can accelerate externally very fast too. We often talk about giving things a speed boost by hitting them with light or matter beams to give it a good initial kickstart, and the handy thing about a black hole is you don't have to worry about overheating anything by slamming energy in too fast. Anything you manage to get a dead center hit on the event horizon of that black hole is not going to splash, and like the planet ship, it can become a Guern ship that never slows down and just keeps speeding up. Acting as a mothership that dispatches smaller colonizing fleets, it can easily slow down, which stops on worlds and build beaming stations to feed their dark mother, who can obtain highly relativistic speeds, zipping through galaxies and leaving a thick trail of colonies in its wake. Like the planet ship, you can always abandon it if you don't want to do the next long voyage, or can't aim it at another galaxy you can reach. Like the planet ship, it has a huge onboard power system that could support a civilization for quite some time. Unlike the planet ship, that quite some time is orders of magnitude longer than the normal star-forming life of the universe, and you can crawl down its gravity well too, especially if you've been feeding it lots of stars to slow your own subjective time down. This is a ship that can almost cross the universe, not just from side to side, but from beginning to end. See the Civilizations at the End of Time Black Hole Farming episode for details, though we'll be expanding on that concept next week in Colonizing Black Holes. Alright, so the Quasar Drive gives us basically the ultimate generation ship, suitable for colonizing other galaxies, and fast enough to get us to many millions of them, while carrying enough material and energy to support huge civilizations for the better part of eternity. Indeed, it could be carrying whole stars along with it to use for propellant and living area, if you don't want to hug the thing too closely. I suspect though, you'd keep the whole thing inside some mega-Earth or even Birch Planet arrangement. Build big enough, and you can even cheat some of the time issues by a mix of special relativity from your speed and general relativity from your mass, both slowing time locally, both of which are rather handy when trying to cover intergalactic distances without some form of FTL. Alright, so we've got the methods, but what's the point? I mean, why would we ever build this? Why would you be moving lots of stars? Well, we've got a few obvious reasons first. We just mentioned the colonization aspect, but I suspect you would never need to go this big even to colonize other superclusters. An artificial small black hole of substellar mass is probably something you can make, and is probably more than sufficient at planetary masses. We've got moving stars so they don't collide, or go supernova in places we'd rather they didn't. But to be honest, you probably have the computing capability to be figuring out how to avoid such things with far less effort by acting very early before you're thinking about using stars as engines. Not all stellar engines are for engines that move dangerous stars. The Matryoshka brain, a giant stellar computing engine able to simulate a whole universe, offers you more than enough computational power to be plotting stellar motion and formation of a galaxy accurately enough that you can intervene with minimal actions to prevent novae and supernovae happening anywhere near places that might hurt folks. You might need them occasionally, but not too often. And of course, a Shikata thruster is an innate ability of any of the other stellar engines. A classic Dyson swarm of habitats or a Matryoshka brain can reconfigure themselves to direct some of their energy and produce thrust. They also make phenomenal weapons, but we'll save that for next month. So why would you do it? Two key reasons. First, the big problem colonizing our galaxy and others, and traveling around them, is the sheer distance involved. But a galaxy can be made far more compact, 1,000 light-years across rather than 100,000, or even tighter, to allow far faster communication or travel. If you've got all that calculation and nudging ability along with big engines, you can slowly push everything into tight, stable orbits, and make sure there's no elements likely to go supernova or ram into others. A galactic super Dyson swarm, billions of stars orbiting as tightly as you can get without overheating everyone around a central black hole, or even some far cooler megastructures we'll talk about more next week. The second is that they can reach other galaxies, very distant ones, and they can move a lot of mass. Whether you are sending them there in the first place, or building them in distant galaxies, these are serious bulk freighters that can achieve a large fraction of light speed and carry or drag stars with them. You could use this approach to wrestle many thousands of galaxies worth of matter back home, not as stars. Only red dwarfs could plausibly live long enough to survive the trip from more distant galaxies, and we wouldn't really want to pack stars in too tight for heat worries, but as raw material for building or fueling your megagalactic civilizations. Of course, you might bring a lot of red dwarfs home from distant galaxies, herded along by massive quasar drives, and maybe so many of them that they won't fleets of stars, but whole armadas. Or for feeding the giant dog monster in your basement, but we'll discuss that more next week. So throughout this series, we've been looking at generation ships, especially the impact of them on the culture that might develop inside one that is on a truly long voyage, and there's some great books on that theme, like Gene Wolfe's Book of the Long Sun, Harry Harrison's Captive Universe, Paul Anderson's Tau Zero, Arthur C. Clarke's Rendezvous with Rama, and many more. One of the best of these is Robert Heinlein's Orphans of the Sky, our book of the month sponsored by Audible. Orphans of the Sky is one of the first books discussing generation ships, and written well before the space age, and an inspiration for so many later stories where the crew forgot they were even on a ship. Heinlein, one of science fiction's grandmasters, walks us through just how easy it would be for a generation ship, by its very nature, to get closed off from the outside world, and indeed, as we've seen, the best designed generation ship, utterly self-sufficient for incredibly long times, are where this could happen the easiest. You can pick up a free copy of Orphans of the Sky today. Just use my link in this episode's description, audible.com/Isaac, or text Isaac to 500 to get a free book and a 30-day free trial, and that book is yours to keep, whether you stay on with Audible or not. And if you don't enjoy the book, you can exchange it for another book, no questions asked. But if you do enjoy it, and you will, there are many other amazing books by Robert Heinlein, and you can find them there on Audible too. So we were talking a little about interesting things you can do with black holes today, and next week we'll get into those in detail and show some other advantages they have, which might make black holes, natural or artificial, far more interesting to future space pioneers than planets and stars in colonizing black holes. For alerts when that and other episodes come out, make sure to subscribe to the channel and hit the notifications bell. And if you enjoyed this episode, hit the like button and share it with others. You can also visit our website, isaacarthur.net, to see what other books we've recommended and discuss them on our forums. Until next time, thanks for watching and have a great week.